Hello and welcome to Lab 3. In this lab, the problem was to observe an object falling straight down from rest and then comparing the motion data from that observation with two models. I will talk more about the two models later. For this lab, I recorded my roommate dropping a bag of Cheetos. I then collected the motion data from the video using Tracker. Because the camera was tilted slightly during filming, I had to tilt the axis also, so the y-axis would correspond to the path of the Cheetos. I also moved the axis so the origin corresponded to the initial position of the Cheeto bag. As I said before, I need to make two models to predict the motion of the Cheetos bag. The first model, which you can see here, predicts the motion of the Cheetos without a drag force or air resistance. First of the data that I use is the mass of the Cheetos, which is 56.7 grams. Next, I use the initial position of the bag, which was the origin of my axis. Also, because the bag was dropped from rest, the initial velocity of the bag was a zero vector.
I chose a very small value for delta t compared to the length of the video because the model of Newton's second law is more accurate over small increments of time. I used the acceleration due to gravity on the Earth, which is about 9.8 meters per second squared. The total time of the video was 0.567 seconds. As I said before, this model assumes that gravity is the only force acting on the Cheetos. This means the net force is equal to the weight of the bag of Cheetos. I calculated the magnitude of the weight to be the product of the mass of the bag of Cheetos and g, the acceleration due to gravity. The direction of the gravity force is in the negative y direction, so the net force is negative as well. Here's where Newton's second law comes into play. According to Newton's second law, the final velocity is equal to the initial velocity plus the net force over the mass of the object times the change in time. To predict the new position for each time step, I use the equation that the final position of the object is equal to the initial position plus the velocity times the change in time.
This is the position versus time graph I created that shows the observed data in the first model data. One would expect the model to overpredict the distance the Cheetos would fall in the given time, since it does not take into account the drag force that would slow the Cheetos down. My graph, however, shows the opposite. Because of this, adding in the drag force would only cause the two to further differ. Let's take a look at the next model. This model takes into account the drag force of model. This model takes into account the drag force on the bag of Cheetos, not just the force of gravity. The drag force is proportional to the magnitude velocity of the object squared and in the opposite direction of the velocity. Therefore, to calculate the drag force, I squared the magnitude of the object's velocity and the direction of the velocity and multiplied it with -1 and a constant I called b. I then added this drag force into the equation for the net force. This way, the net force in the bag of Cheetos is the gravitational force plus the drag force. As you can see, adding in the drag force causes the model's predicted final position to be less than that of the previous model. Had my first model over-predicted my observed data, I would have adjusted b to the new model to fit my observed data. Although there was an error with my model, the general curve of the model is similar to my observed data. Terminal velocity occurs during freefall when the drag force on the object equals the force due to gravity. This means that when an object reaches terminal velocity, its net force equals 0. Like we saw in Lab 1, when the net force on an object is 0 and it is moving, it moves with a constant velocity. Terminal velocity can be seen on a position time graph where the graph becomes a straight line. Only the model that includes the drag force shows a straight line. Terminal velocity occurs during freefall when the drag force on the object equals the force due to gravity. This means that when an object reaches terminal velocity, its net force equals 0. Like we saw in Lab 1, when the net force on an object is 0 and it is moving, it moves with a constant velocity. Terminal velocity, then, can be seen on a position time graph, where the graph becomes a straight line. Only the model that includes the drag force shows the terminal velocity, since the force due to gravity will never equal 0. Terminal velocity can be seen from here to here, because this is where the graph is a straight line. Thanks for watching.